Good morning students. Today we are going to discuss the topic acid-base titrations. So acid-base titrations comes under the topic of titrometric analysis, in which the major part of the analytes are going to be analyzed by this acid-base titration. We know that pharmaceutical substances fall under majorly weakly acidic or weakly basic in nature. Okay, so thereby we are going to have major part of the titrometric analysis in acid-base titration range, because all these acid-base titrations will give you the most of the easy methods of analysis for pharmaceutical substances. So in this acid-base titrations, you are going to learn about the key terms like acid dissociation constant, acid strength, okay, so acid function, what are the different buffer solutions you are going to use, and what is the self-ionization of the water, how the reaction is going to be completed, and what is the pH is going to affect your titrometry. Okay, so how the acid base reactions are going to give you the neutralization reactions based on the pH of the reaction. Okay, so how this reaction is going to be completed, all these terminologies you are going to see in this today's session. So if you see what are the different types of the acids and what are the different types of the bases. So acid types, if you see, Bronsted acid, Lewis acid, mineral acid, strong acids, organic acids, okay, similarly weak acids, and finally super acids. So all these types of the acids are going to be present in the substances. Similarly, if you see the base types also, Bronsted base will be there, Lewis base, organic base, as well as strong bases and super bases, and one more category, that is non-nucleophilic type of the bases are also there. Okay, so all these types of the substances are going to be analyzed by acid-base titrations. Most of the compounds are going to be used by the indicators, okay, because in acid-base titrations we can perform both manually as well as instrumentally also. So if you go for the visual methods, you need to use some indicators, whereas if you go for the instrumental methods, thereby you are going to measure the potential of the analyte. So by the titration curves, we are going to find out the what is the end point of the titrometric reaction. Okay, so whenever these acid-base titrations are going to be performed, those studies are going to be called it as acidimetry as well as alkalimetry. So if you see what is acidimetry and what is alkalimetry, so alkalimetry and acidimetry is a kind of volumetric analysis in which the fundamental reaction is a neutralization reaction. That means ultimately the final endpoint is going to be a neutralization reaction. Okay, either weak acid strong base or strong acid weak base, whatever it is, the ultimate finally it is going to give you the a neutralization reaction. Okay, so alkalimetry, which is a specialized analytical use of acid-base titration to determine the concentration of a basic substance. So if you can easily remember that alkali means base, right? So alkalimetry is a type of analysis which is going to determine the concentration of basic substances. So acidimetry means same, vice versa. It is also called as acidometry also, which is the same concept, that is acid-base titration for determining the acidic substance. Okay, so titrant or titrator, we know all these terminologies in our basic titrometric introduction lecture also. Okay, so what is a titrant, what is a titrator? So which is a standard solution of the known concentration. That means already a primary standard or a secondary standard which is already a standardized one. Like that, a titrant or a titrator should be there. So which is actually example for the titrant solution, that is a sodium carbonate solution, because it is a primary standard. So whether in acidimetry or alkalimetry, we are going to use these types of the titrant solutions. And titrant, that means analyte solution, that is a solution of unknown concentration. Okay, so these two types of the solutions will be there in acidimetry as well as alkalimetry. So whenever we are going to analyze either acid substance or basic substance, the method has to be optimized, right? So we should know the basic properties of the compound and what are the different types of the titrants you need to titrating solutions, and all this information you should have in your hand. So before starting the titration, you should know a suitable pH indicator must be chosen, because all these are the visual methods. pH indicators are need to be selected. So the equivalence point of the reaction, here you can see the equivalence point of the reaction. That means what is that? The point at which the equivalent amounts of the reactants have reacted will have a pH dependent on the relative strengths of the acid and base used. Okay, so where the equivalence is going to be happen by the stoichiometry of the reaction. So the pH of this equivalence point, can be estimated by using this following types of the rules. So what are those rules? A strong acid will react with a strong base. So when a strong acid react with a strong base to form a neutral pH, that means neutral pH means it is a 7, right? So 7 pH solution, it is going to give a neutralization reaction when a strong acid and strong base. Okay, so this equivalence point, how we are going to determine, these are also depend on the type of the analyte we are going to use and type of the titrant solutions we are going to use. So these types of are the following rules we are going to consider while going for the titrometric analysis. Okay, so second one, a strong acid will react with a weak base to form a acidic solution. So whenever a strong acid is going to react with a weak base, ultimately the neutralization reaction is going to happen at the pH less than 7. Okay, and third one, a weak acid will react with a strong base to form a basic pH. That means the pH of the solution, final end of the solution will be more than 7. Okay, so these three rules are going to play a very important role while performing the acid-base titration. That means at getting the equivalence point. So basically after getting the equivalence point only, the end point is going to be detected by the indicators. We know all these things. Okay, so here some of examples of the indicators used in acid-base titrations. If you see the indicator, here we have listed out some of the indicators. Those are having different colors at different pH ranges. Okay, so if you take 𝘂𝙀𝙎𝙬, it is yellow on the acidic pH, whereas it is going to be used in the pH range of 0 to 1.6. That means very strong acids are used, means in such cases you are going to use this 𝘂𝙀𝙬𝙬. Then color on the basic side means at the end point you are going to see whenever the pH is going to be neutralized. Afterwards you are going to see the violet color of this 𝘂𝙀𝙬𝙬. Okay. Similarly, if you see alizarin yellow, generally it is yellow in the acidic range, whereas it is going to be red in the basic side. So highly basic solution, that means which are having the 10.1 to 12 range, highly strongly alkalimetric solutions is going to be used. Then you are going to use this alizarin yellow. Okay, so acid-base titration is performed with bromothymol blue indicator when it is a strong acid and strong base. So these type of the indicators are used whenever there is a type of the analyte is going to be there, based on the strength of the acid also it is going to be used. Okay, so acid-base titration generally it is performed with bromothymol blue. When it is a strong acid, is going to be titrated with the strong base. Okay, so both are strong, then bromothymol blue is the suitable indicator. Next, coming to the phenolphthalein solution, which is going to be used while performing a weak acid and strong base. Okay, so whenever our analyte titrant is an weak acid and we are going to titrate with a strong base solution like NaOH, then we are going to use the indicator phenolphthalein solution. Okay, so whenever a strong acid and weak base is going to be used, that means titration between these two is going to happen, then what is the indicator preferred? That is methyl orange. So methyl orange is going to be used at the case of strong acid and weak base. Okay, so if the base is off the scale, that means out of the scale, that means high pH, okay, high basic pH range, a pH of more than 13.5 and acid has a pH of more than 5.5, then we are going to use the alizarin yellow indicator may be used. So already we have discussed that alizarin is going to be used at the high pH range values. Okay, so if the base, that means which is 10.1 to 12, and also if it is more than 13.5 also, and then if the acid has a pH of more than 5.5, that means strong acid is going to be there. So in such cases you need to be used alizarin yellow as the indicator, that is the preferred one. So on the other hand, if the acid is of the scale, that means if the very strong acids, that means pH is less than 0.5. Okay, so and the base has a pH of less than 8.5, then a thymol blue indicator may be used. So this thymol blue is used whenever there is a acid is very high. Okay, acid strength is very high, then go for the thymol blue solution. So here there are some of the key points are highlighted. If you see, when a weak acid reacts with a weak base, then the equivalence point of the solution will be basic if the base is stronger and acidic if the acid is stronger. Here you can see the two cases, that means vice versa. When a weak acid reacts with a weak base, what happens? The equivalence point will be basic if the base is stronger, okay, and acidic if the acid is stronger. Based on that, if both are of the equal strength, then what happens? The equivalence, if both are of the equal strength, then the equivalence pH will be neutral. So however, weak acids are not often titrated against the weak bases. So in case of weak acids or weak bases, they are not at all going to be titrated with each other. Okay, so because the color change here shown with the indicator is not often quick, because that means you are not going to see very sharp endpoint, therefore very difficult for the observer to see the change of the color. That's why generally weak acids are not going to be performed, but if there is no option, then go for it. Okay, so the point at which the indicator changes the color is called the endpoint. We know that equivalence point means the stoichiometry of the reaction is going to be completed. That means the number of moles of the analyte is going to be completely neutralized by the number of moles of the titrating solution. Okay, so thereby the stoichiometry of the reaction has been completed. Whereas if you see the endpoint means the point at which the indicator changes its color. Okay, so the indicator change color is happened at the endpoint level. So a suitable indicator should be chosen, preferably one that will experience a change in color. That means an endpoint close to the equivalence point. So the equivalence point as well as endpoint should be very close, which are having very closeness. That means very accurate values should be there. Only plus or minus 0.05 ml or like that. That much of accuracy should be, the level of accuracy should be very high. Okay, so for this purpose we need to be select the type of the indicator, how we are going to be used for the type of analyte we have taken into the analysis. Okay, thereby what is the pH of the solution, what is the pH of that analyte, and what is a suitable indicator we need to use. All these things are going to be considered. As we know that titrometry is going to be performed by using burette and conical flask. So first of all, the burette has to be rinsed with the standard solution and the pipette with the unknown solution. So and the conical flask with the distilled water. That means all these are the basic concepts. Okay, so in conical flask we are going to take the analyte. Secondly, how we are going to analyze, that means how we are going to clean all the glassware with the solutions, and how the unknown concentration of the solution is going to be taken, pipetted out, and then how we are going to perform all these things. Actually we have learned in the introduction to the titrometric analysis. Okay, so in this we are going to learn about only the how the acid base titrations are going to be performed. So at the equivalence point, the weak acid, actually the weak acid is consumed and converted into the conjugate base. Okay, then what happens? The pH will be greater than 7 and can be calculated from the equation which is derived from the following relation. That is, so whenever a titration is performed between an acid and base, whether it is a weak acid or weak base, or then at the equivalence points what happens? The weak acid is consumed and converted into a conjugate base. Then the pH will be greater than 7 and can be calculated from the equation. So what is that equation? This is pH plus POH equal to 14. Okay, so what is actually a pH? Potential of hydrogen ions, H plus ions. So POH means potential of OH minus ions. So when these potentials are going to be clubbed, it should be equal to the 14. So here at the equivalence what happens? CaVa equal to CbVb. CaVa means, Ca means concentration of the acid and Cb means concentration of the base. Okay, so what is Kw here? Dissociation constant of the water. So thereby we are going to learn about this equation, that is Ka into Kb equal to 10 to the power of minus 14. So what is Ka? Dissociation constant for the acid, whereas Kb means dissociation constant for the base. So these two products are going to give you the Kw value, that means dissociation constant for the water in case of this acid base titrations, because finally we are going to get the neutralization reaction thereby. Okay, so you need to know that when an acid neutralizes a base, the pH may or may not be neutral, and that means it may not be equal to pH 7, and this pH depends on the strength of the acid and base. That means how much strength of the acid, the acidity or basicity of the compounds you are going to use. Okay, so if you see the, for example, of a titration of a weak acid with a strong base, normally not only a weak acid with a strong base, so any type of the acid base titration if you see, so these are the general points you are going to learn about. So what are those means? Here just an example I have taken. So if you see, on y-axis pH is taken, on x-axis volume of the titrant has been taken. Okay, so titration of a weak acid with a strong base, that means you are going to take weak acid in a conical flask and strong base in a pipette, in burette. Okay, so if you see the curve, it is going to happen. So if you take the examples of a weak acid and a strong base, weak acid you can take the example of an acetic acid, and strong base it is an example of a NaOH. Okay, so if you see that, then initially we are going to have 0 ml of the NaOH, that means no NaOH is added. At that point we are going to take the ml of only weak acid in the conical flask. So in that case the pH is going to be around 2 to 4, that means in between around 3. Okay, so go for, while adding sodium hydroxide solution gradually, okay, then the titration is going to be carried out, and before going for the equivalence point you are going to see the rise in the pH, because it is a strong base. You are going to see the rise in the pH. Okay, the curve is going to be raised here. So afterwards you are going to see the equivalence point, that means the stoichiometry of the reaction has been completed. The number of analytes are going to be neutralized by the hydroxyl ions present in the NaOH. Okay, so at this equivalence point what happened? The stoichiometry has been completed. So afterwards, due to the presence of the indicator, you are going to see the end point of the titration. Okay, so even though after getting the equivalence point, if you go on adding the excess amount of the NaOH, you are going to see the curve like this. So that's why it is a plateau. That means after equivalence you are going to see a no change in the pH. That means all the ions have been consumed. Okay, so that's why the curve is like this. So neutralization has been achieved. So based on this type of analytes and what are the different types of the titrating solutions we are going to use, the reaction is going to takes place. So in acid base titrations we are going to focus majorly what type of the different types of the acids we have discussed, that what is Bronsted, Lewis acid, all these things. So for this there are some theories are there. For that purpose they have you need to know about what is a Lewis acid, okay, what is a Bronsted acid, like this. So here we are going to learn about a Arrhenius concept. So Arrhenius has given one concept for this. So according to this concept, what is going to be there? Acids or the substances that dissociates in aqueous medium to give H plus ions. Okay, what Arrhenius has told, that acids are the substances which dissociates in aqueous medium to give H plus ions, and bases are the substances to produce the OH minus ions. Okay, so H plus ions are going to be produced by the acids, that means protons, and OH minus ions are going to be given by the bases. Okay, so in ionization of an acid and ionization of a base, if you see for example hydrochloric acid is there. So hydrochloric acid, while in water, if you see whatever the strength of the hydrochloric acid is there, then you can see the ionization is going to happen like H plus plus Cl minus. That means it is going to generate H plus ions and chloride minus ions. So this acid is going to be ionized like H plus ions and Cl minus. Whereas if you see the ionization of the base NaOH in water, if you see, then it is going to be ionized into Na plus OH minus ions. So this OH minus ions are going to give you the basic range. So H plus ions are going to give you the acidic range. That's why Arrhenius has given the concept that acids or dissociates into H plus ions in aqueous medium. Okay, so in aqueous medium you should remember that, and bases are going to give you the OH minus ion. Okay, so thereby you are going to see different types of the proton donors, proton acceptors in different types of the elements or ions we are going to analyze. But there are some drawbacks for the Arrhenius concept. So what are those? Applicable only to the aqueous solutions. So if you are going to use another type of the solutions like non-aqueous solutions, then Arrhenius concept is not going to work, because especially we have mentioned here that acid is going to be dissociated or ionized in the aqueous medium. So this Arrhenius theory is applicable only to the aqueous solutions only. Okay, so it fails to explain the acidic nature of the substance like CO2 and SO2, which does not contain H plus, and for bases which does not contain OH minus like sodium carbonate and ammonia. These are the basic solutions, but these don't dissociate into OH minus ions, right? And similarly CO2 and SO2, these don't contain the H plus ions, these don't dissociate into H plus ions, but still these are acidic and these are basic in nature. That's why Arrhenius theory is applicable only to the aqueous solutions only. This is a drawback for this concept. So now coming to the next concept, that is Bronsted-Lowry concept. So Bronsted-Lowry, according to this theory, what is an acid? Okay, so acid is a substance that is capable of donating a proton, and bases are the substances capable of accepting a proton. Okay, so according to Bronsted, acids are donating a proton, whereas bases are capable of accepting a proton. Okay, so acids are the proton donors and bases are the proton acceptors. So in this way Bronsted-Lowry has defined what are acids, what are bases. So they have given one example for this. So ammonia in water, if you see how this is going to give you the that means proton donating a proton and accepting the proton. Okay, so ammonia is a base. So if you see this base, it is going to be converted into a conjugated acid, and OH minus is a conjugate base. Okay, similarly if you see acid CH3COOH in water, if you see it is going to give you a conjugate base, that is CH3COO minus. Even though here also ionization is going to take place, but they have defined that it is going to be a how the protons are accepted and how the protons are donated. Okay, so this is a theory of the proton in terms of the protons. So a conjugate base is an ion or molecule left after an acid donates a proton. Here they have mentioned that a conjugate base. So for this an example here, CH3COO minus. CH3COO minus is an ion or molecule left after acid donates a proton. Okay, so a conjugate acid is an ion formed after accepting the proton. Okay, so these pairs of the substance which are formed from one another by the loss or gain of the proton are called conjugate acid and conjugate base. Okay, so thereby this is going to called as conjugate acid and base pair. Similarly vice versa, conjugate base and acid pair. Okay, so these are the different concepts we are going to see while defining the what is acid and what is base. So if you see the limitations of this theory also, substances like BF3 and aluminum chloride AlCl3 do not have any hydrogen and hence cannot give a proton, but are known to behave as acids. Okay, so here are the some of the limitations you are going to see for this Bronsted-Lowry theory. Then coming to the Lewis concept. So if you see this Lewis concept, according to this theory, an acid is a substance which accepts a pair of an electron. So here Lewis has defined again acid bases as in terms of the electrons. Okay, so Arrhenius has defined in terms of the ionizations, and Bronsted-Lowry has explained in terms of the protons. Now Lewis has defined in terms of the electrons. Okay, so according to this theory, what happened? an acid is a substance which accepts a pair of an electron, and base is a substance which donate a pair of electron. Okay, so this is how Lewis has defined, and limitations for this theory are also there. So let us see what are those. Relative strength of acids and bases cannot be explained by this concept, because relative strengths of the acids and bases means what? Actually, the strength of an acid depends upon its tendency to provide the proton, or more precisely hydroxinum ion. Okay, that means H3O plus hydroxinum ion is going to be present. So strong acid, actually strong acid refers to that equilibrium which lies very much to the right hand side. That means hydroxyl ion. So you are going to H3O plus is going to C. Okay, and the backward reaction takes place almost to a negligible extent. So it is not going to be a backward reaction. So only once a strong acid is going to be react with any type of aqueous solution, you are going to see hydroxyl ions, and in case of hydrochloric acid you are going to see the chloride ions. So when it comes to the weak acid refers to the equilibrium lies very much to the left hand side, and means dissociation of the acid to give H plus or H3O plus is very, very small, because it is a weak acid. Okay, so that's why this relative strength of acid as well as relative strength of the bases are not at all going to be explained by this Lewis concept. So the strength of these acids or bases are going to be varied. Then ultimately what happened? The strength of the base will depend upon the availability of the OH minus ion. They have concluded that the basic strength is going to be depend upon the availability of the OH minus ions. So in case of strong base, equilibrium lies very much to the right hand side, and the backward reaction takes place almost to a negligible extent. That means here also, if it is a very strong base. Okay, so in previous slide we have also seen that it is a strong acid. Similarly here also it is a strong base. Then also the reaction is not a reversible reaction. So here NaOH is going to give you the OH minus ions. Similarly in case of weak base, if you see, the equilibrium mainly lies to the left hand side. Okay, so weak acids, weak bases are going to be play a different role. That's why the relative strength of those acids or bases cannot be explained by this Lewis concept. Okay, so strength of the acids and bases will depend on the degree of the dissociation. So if you see the degree of the dissociation, we know that Ka, Kb, that means acid dissociation constant, basic dissociation constants. Okay, so these strength of the acids and bases will depend on the degree of dissociation. So higher the degree of dissociation of the acids or bases, stronger will be the acids and bases. So that means if strong acids or strong bases are used, then the degree of dissociation will be more. Okay, so based on all these concepts, they have concluded one law of mass action. Okay, by which scientists 𝙂𝙖 and 𝙂𝙖 in 1867 started a law of mass action. So according to the law, actually what has happened means they have what has defined by the is the velocity or rate of chemical reaction. The velocity or rate of a chemical reaction is proportional to the product of active mass reacting substances. We know that substrates are there. That means those reactants. Substrates means reactants and products. Okay. So similarly, law of mass action, what it is going to give you the information, that is the velocity or rate of this chemical reaction is proportional to the product of the active mass reacting substances. So what are those? So if you see the water, if you take the water molecule, then it is going to dissociate H plus plus OH minus ions. So the velocity of the rate of this reaction is going to be a product, that is H plus into OH minus. So already we have seen in the previous slide how we are going to define the ionic product of the water, KOH into KW, KA, like that. Okay, so thereby you are going to see in all the neutralization reaction how this law of mass action is going to be applicable. Okay, because all these concepts are going to have some of the limitations and drawbacks on one another. That's why acid base reactions are mostly going to be defined by this law of mass action only. So if you see this ionic product of the water, okay, so these two are the scientists, okay, where they found that the most highly purified water possesses a small but definite conductivity. We know that water is going to be different types, like demineralized water, distilled water, tap water, okay, and all the water which is going to be used for the electrical appliances, okay, that means that is a acidic water. So different types of the water will be there. So highly purified water, actually if you see highly purified water which is going to be used for the preparation of the all the saline solutions, okay, so if you take that, it is going to possess a small but definite conductivity will be there for this purified water. So water must be slightly ionized and in accordance with this equation. That means we know that H2O is going to be dissociated into H plus OH minus ions. So thereby if you see the hydroxyl ions H3O plus, okay, so those ions are also going to be formed in reversible reactions. Okay, so whenever weak acids or weak bases are going to be titrated with strong acids or strong bases, then you are going to see hydroxyl ions, then H3O plus ions. Thereby you are going to have some of the difficulties while performing this acid base titrations. Okay, so if you see this ionic product of water, then you can have different types of the equations we can apply in this acid base titrations. Okay, so applying law of mass action, you can calculate what is Ka value. Okay, so Ka equal to, that means acid dissociation constant, that equal to concentration of the H plus ions into concentration of the OH minus ion divided by concentration of this water molecule. That means reactants or substances which are going to react. Okay, so the product of these two products, H plus and OH minus ions, divided by the product of the reacting substance. Since water is slightly ionized in dilute solutions, the concentration of the undissociated water may be considered as a constant value. Here that means undissociated water, if anything is there, completely it gets H plus OH minus may not be possible because it is a dilute solution. So thereby you can see it is represented as K1. So H plus ions and OH minus ions are going to be considered here. So thereby if you take this K1 value and if you cross multiply this, Ka into K1 equal to concentration of the H plus ions into OH minus ions. So here they are going to convert this Ka into K1, that is as Kw. So Kw equal to concentration of the H plus ions into concentration of the OH minus ions. So this Kw they have defined that as ionic product of the water. So at 25 degrees centigrade, this Kw value will be 1 into 10 to the power of minus 14. Okay, so as we are already discussed that POH plus pH equal to 14. So if you apply all these equations, you are going to see the value of the ionic product of water is going to come around this 1 into 10 to the power of minus 14. Okay, so this is about the law of mass action and different concepts which are going to define the acids and bases. Now coming to the another type of complicated equation, that is Henderson-Hasselbalch equation. So in order to calculate the pH of a buffer solution during the dissociation of a weak acids, so if you take a strong acid and strong base or a strong base with a strong acid, if you titrate these two type of the reactions, your endpoint will be very spontaneous. Okay, thereby you can easily identify the endpoint and calculate. But whenever you are going to see weak acids or weak bases, then the dissociation will be very less. So in those cases some of the problems are going to arise. So in order to solve that, how we are going to use the different types of the concepts here. One of the equation, that is Henderson-Hasselbalch equation. So in this, a weak acid, they have taken one example, that is it does not entirely dissociate. We know that because the acid strength is very less, that's why it is not going to dissociate completely. So the buffer solution has the capacity to tolerate the pH fluctuations when a little amount of the acid is added. So whenever a weak acid is going to be not completely dissociated, then the buffer solution is going to play a role when an acid is going to be introduced. So it is going to, the pH fluctuations whatever are there are going to be compensated by this buffer solution. So for this purpose they have given one equation, that is pH equal to pKa plus log of to the base 10 concentration of the A minus and HA, that means salt by acid or acid by salt. Okay, here pH equal to pKa means we need to consider that, okay, it is acid by salt only. So A minus means it is acid and HA means it is a salt. Okay, so this is the Henderson-Hasselbalch equation. The derivation of the equation is different. Just if at all any calculations are there, you need to calculate what is pKa value if the pH has been given, okay, in calculation point of view, and what are the different types of the acids they have used, and here they have given the logarithmic scale. That's why the calculations are going to be based on salt and acid. So thereby logarithmic tables you need to take help for that calculation also. Here if you see, A minus is the molar concentration of the conjugate base and HA is the molar concentration of the weak acid, because here you are going to see the after ionization. Okay, so after ionization A minus will be the conjugate base, and after ionization HA will be the concentration of the weak acid. Okay, so before that it is different, after reaction it is different. Now coming to this Henderson-Hasselbalch equation, the limitations. So the most important assumption in this equation is the concentrations of the conjugate bases of the acid will remain constant during the equilibrium, because it is assumed that the concentration of the conjugate base of the acid will remain constant only at the equilibrium state. And the importance of this water hydrolysis and its impact on the pH of the entire solutions are completely ignored, because water is going to be hydrolyzed and it is going to be forming the H3O plus ions. Okay, so thereby the pH of the final solution is going to be ignored. So that is one of the major drawback of using this equation. And similar to this, the base hydrolysis and acid dissociation are similarly disregarded. So when dealing with the strong acid and bases, the equation's underlying premise could break down. That means while using the strong acid and strong base, this equation is not at all useful. But whenever where weak acid or weak bases are going to be used, it is going to play a key role. Okay, so if you see what is the pH example for calculating this Henderson-Hasselbalch equation, let us take one example. What is the pH of a buffer solution made from 0.2 molar HC2H3O2, that means CH3COOH, acetic acid, and 0.5 molar CH3COO minus. Okay, that means it is a conjugate base. So it has an acid dissociation constant of acetic acid of 1.8 into 10 to the power of minus 5. So how we are going to solve this? Let us see. So solve this problem by plugging the values into Henderson-Hasselbalch equation for a weak acid and conjugate base. So pH, we know that pH equal to pKa plus log of salt by acid, acid by salt. That means here base is going to be there. It is a conjugate base and it is a weak acid. So pH equal to pKa plus log of conjugate base, that is H3COO minus divided by acid. Okay, so pH equal to minus log of, that means whenever you are going to see 1.8 into 10 to the power of minus 5, and it is going to be substituted like this. Okay, so thereby after calculation of logarithmic tables and sorting out, you are going to get the pH as 5.1. Okay, because for this purpose calculations you need to use the logarithmic tables. So while in exams also, thereby you are going to have simple calculations, like we know that log 100 equal to 2. Okay, like that simple derivations you are going to get it. Thereby pH has to be calculated, and Henderson-Hasselbalch equation will help you to calculate the pH of the solutions where weak acids are going to be analyzed. Okay, and one more encounter problem in acid-base titration, that is common ion effect. So it is a degree of dissociation of an electrolyte suppressed by the addition of another electrolyte. Okay, we know that common ions means the same ions which are going to be present with which is not required in the solution. Okay, so the dissociation degree is going to be suppressed by the addition of another electrolyte containing a common ion, or dissociation of comparatively weak electrolyte suppressed by a strong electrolyte. Okay, so vice versa it is going to happen. So for this common ion effect, we have given one example, that is dissociation of NH4OH is diminished by the addition of salt, that is ammonium chloride, which furnishes the common ion NH4 plus. Actually the ammonium hydroxide, it is a weak base, right? So the dissociation is going to be diminished by addition of the salt ammonium chloride. It is going to be added, which furnishes the common ion NH4 plus. We know that NH4OH is a base, so it is going to dissociate into ammonia plus OH minus ions. So according to the law of mass action, what happens? K equal to NH4OH, NH4 concentration into OH divided by NH4OH. Okay. So by applying this law of mass action, K is going to be called it as equilibrium constant. Now a strong electrolyte, if we add a strong electrolyte, that is ammonium chloride, is going to be added, then what happens? Ammonium chloride is going to be dissociate into ammonium plus chloride ions, NH4 plus Cl minus. So what happened here? The value of concentration of NH4 plus ions will increase, and therefore concentration of the OH minus ions will decrease, because base are going to be increased by the addition of this ammonium chloride. Thereby the OH minus ions will decrease to maintain the equilibrium. Finally what happens? The ionization of NH4OH is suppressed, and hence the release of OH minus ions is going to be decreases. So the common ion effect provides a valuable tool controlling the concentration of an ion furnished by the weak electrolyte. Okay. So in case of weak acids or weak bases we are going to use. So sometimes this common ion effect will give you most precise results, and sometimes it is a disadvantage also. We need to have a basic knowledge which type of the ions we need to add. Okay. To increase the degree of dissociation, and how the pH is going to be maintained at the equilibrium state. Okay, these two concepts has to be considered in mind while adding the different types of the electrolytes to the solution. Now coming to the universal indicator. So we know that the terminologies are going to be there in this lecture, that is amphoterism, and different types of the indicators we are going to use for the acidic range and basic range. So now amphoteric solvents, that means both, like buffer solutions, they provide both protons and as well as electrons. That means they are going to act as either gain of electrons or acceptance of the electrons, donating the electrons or acceptance of the electrons also. So in this case, amphoteric solvents, whenever you are going to use, you need to use some different types of the indicators. So here we are going to list out one indicator, that is universal indicator. So what is a universal indicator? So by mixing suitable indicators together, okay, different types of the indicators together, changes in the color may be obtained over a considerable portion of the pH range. Okay, so whenever solutions are going to be different for for acidic pHs, if you are going to analyze, titrate, then suddenly the pH range is going to be different. So you cannot optimize the indicator, which type of indicator you can select. Okay, so the pH is suddenly steep increase is going to be there, suddenly steep down is going to be there. So in such cases, an universal indicator will going to help you. So for this purpose, what we need to do is we need to mix. Okay, so the different compounds are going to be mixed such that these are called as universal indicators. So they are not suitable for the quantitative titrations, but may be employed for the determination of the approximate pH of a solution by the colorimetric method. That means colorimetry method is a different based on the color we are going to use in instrumental methods of the analysis. So in those cases we are going to use this universal indicator. So for this purpose we have given one example, that is what is a universal indicator, how it is going to be prepared. That is dissolving 0.1 gram of the phenolphthalein, 0.2 grams of the methyl red, 0.3 grams of the methyl yellow, 0.4 grams of the bromothymol blue, 0.5 grams of the thymol blue in 500 ml of the absolute ethanol. Okay, and adding NaOH solution until the color is yellow. That means the pH is going to be slightly adjusted, and thereby you are going to get an universal indicator solution. So this, for this universal indicator, you are going to see the color changes. How you are going to see this means, if you are going to get the pH in this range, that means 2, 4, 6, 8, 10, then colors are going to be like this. We know that acidic range you are going to see the red color and thereby orange. Okay, so by go on increasing the pH you are going to see yellow, green, blue. So similarly the universal indicator is also going to give you at the low pH levels these are the colors, and high pH levels these are the colors. Okay, so this will help in colorimetric analysis. Now, after knowing all this, what are the acids, bases, different concepts, okay, so you are going to have a basic knowledge, okay, what type of the acids are going to be present. That means different types of acids, how they are going to, weak acid or strong acid. So okay, so what type of the titrating solutions you need to use for getting the high degree of the dissociation. Okay, so all these are going to be based on the different types of the concepts and ionic product of the water, and how these aqueous solutions are going to affect, okay, your titrometric analysis. Now coming to the important, that is theory of the indicator. So here we have listed out the three theories, that is Ostwald theory, second one quinonoid or resonance or chromophore theory, third one physicochemical theory. So Ostwald theory, what is this means? According to the Ostwald theory, the color change of any indicator is due to its ionization. Ostwald, what they have proposed, that is, according to theory, the color change of any indicator is due to ionization. So these three theories, Ostwald theory, chromophore theory or physicochemical theory, are about the indicators. So that means what type of suitable indicator we are going to use. So that is about, okay. So the unionized form of indicator has different color than its ionized form. We know that indicator is also going to be ionized in acidic range or basic range, and in unionized form it is going to have one more color, in an ionized state it is going to have a different color, right? So an indicator is either a weak acid or a weak base, so its ionization is highly affected in acids and bases. So if an indicator is a weak acid, its ionization would be very much low in acids due to common H plus ions, while it is fairly ionized in alkali solutions, okay. So in the same way, if the indicator is a weak base, then what happens? Its ionization is very large in acids and low in alkaline solutions due to the common OH minus ions, okay. So let us take examples of the two important indicators. As we all know, phenolphthalein is a well-known indicator, which is a weak acid, and methyl orange is a weak base, okay. Phenolphthalein is a weak acid and methyl orange is a weak base. Let us see the examples. So if you see the phenolphthalein, it can be represented as HPH, and it ionizes in solution into small extent. Let us represent this phenolphthalein as like this, okay. So in this case, if you see, this HPH is going to be ionized into H plus ions and pH minus ions. So in weakly acidic solution, it is going to be colorless. That's what they have shown here in the figure, okay. So in this figure, if you have seen, the pH 7 is colorless here, okay, in this flask, pH 7. Whereas if you see in pH 10, it is pink color. That means at the basic side it is pink color. So applying the law of mass action, the dissociation is going to be calculated based on H plus into pH minus divided by HPH, okay. That means product concentration divided by reactant concentration. So the undissociated molecules of this phenolphthalein are colorless, while pH minus ions are in pink color. That means dissociated ions are in pink color. So in presence of an acid, the ionization of this HPH is practically negligible, as the equilibrium shifts to the left hand side due to high concentration of the H plus ions, okay. So here what happens in acid, if acid is present in your analyte, then what happens? High concentrations of the H plus ions are going to be present. Then left hand side reaction will be there. That means it is going to be unionized state. So HPH is going to be more. Then the solution would remain the colorless, okay. So on addition of the alkali, that means we are going to add the OH minus ions. So hydrogen ions are going to be removed by OH minus ions. So in the form of water molecules or whatever it is, strong bases or we are going to use, and the equilibrium shifts to the right hand side. That means this side, okay. So this means this hand you are going to see. Thus the concentration of this pH minus ions increases in solution, and thereby you are going to see the pink color in the solution. That's what it is going to happen, okay. Now let us see the methyl orange. So if you see the methyl orange, it is pH 2 in the acidic medium, and pH 7 it is somewhat yellow in color. So methyl orange, it is very weak base and can be represented as MbOH. Let us assume that. So it is ionized in the solution to give Me plus plus OH minus ions. So if you see the methyl orange, in acidic it is a weak base actually. So in weak base it is yellow in color, and if you see here in acidic range it is going to be red in color. So applying the law of mass action, K equal to Me plus OH minus ions product divided by MeOH. So in presence of an acid, this OH minus ions are removed in the form of water molecules, and the above equilibrium shifts to the right hand side, this one. So sufficient methyl ions are produced which impart red color to the solution. If you see in this graph, okay, here it is the red color. So sufficient red color is going to be produced. Then on the addition of the alkali, what happened? The concentration of the OH minus ions are going to be increased, and the equilibrium shifts to the left hand side. That is, the ionization of MeOH is practically negligible side. Thus, the solution acquires the color of unionized methyl orange molecules, that is yellow in color. Okay. So you are going to see different types of the colors for these two indicators in different pH ranges. So this is the Ostwald theory has given unionized form, ionized form. Now coming to the chromophore or resonance theory. So indicators are the mixtures of the two tautomers in the equilibrium. So what they in chromophore theory, what they have defined, that is indicators are the mixtures of the two tautomers in the equilibrium. And tautomeric form, what happened? It possesses the quinonoid structure. Example, if you see phenolphthalein itself, okay. So whereas the other possess simply benzene ring or benzenoid form. So indicators are generally, we have discussed that these are either weak acids or weak bases. So indicators, they show a change in color from a predominantly acidic medium to a alkaline medium. So if you see the example of the phenolphthalein, so in this, here it is a benzenoid form and it is going to be equilibrium with the quinonoid form. So let us consider the case of phenolphthalein and methyl orange. Same, phenolphthalein is most popular diprotic acid indicator. Okay, weak acid, we have already discussed about this. So it has benzenoid form in acidic medium and thus it is colorless, while it has quinonoid form in alkaline medium which has pink in color. Okay, so this is the difference in the tautomers. So this is what they have given in this resonance theory. This is also called as chromophore theory or quinonoid theory. So because how the tautomers are going to give you the different color changes in the pH values. Now coming to the third one, that is physicochemical theory. So physicochemical theory, if you see, the color changes occur due to the increase in the concentration of certain ions. We know that increase in the concentration causes the appearance of color, right? Whereas decrease in the concentration of some ions causes disappearance of the color. This is general statement we are going to see. An appearance of any new color is going to be formed. So methyl orange is a weak base and it is yellow in color. We have already discussed that. So addition of this proton gives a cation which is pink or red in color. Okay. So for this, that means it is a physicochemically it is going to give a different color. Already dissociation, everything is going to happen, but in ionized form the physicochemical properties are different, whereas ionized state the properties are different. Thereby you are going to see the different colors. Okay. So if you see the examples how these physicochemical theories are going to be affecting the pH range. If you see more acidic side, so battery acids. So whatever the different types of the batteries we are going to use in solar systems or in our electrical equipments. Okay, so those battery acids are going to have very highly acidic nature. So in this case you can see the more acidic nature, color is going to be very red in color. Thereby if you go on increasing the pH, the vinegar solutions are going to fall in the range of 3. Okay, then the black coffee is going to have the color pH ranges of around 5. Okay, now distilled water is going to have at the range of 6 to 7. Okay, and handmade soaps, we know that these are basic in nature, so they are going to have the 9 to 10. Okay, and ammonia is going to have the pH 11 to 12, and thereby sodium hydroxide is going to have the high pH value more than 12. You are going to see. So like this, the physicochemical properties are also going to give you the different pH ranges which are going to affect the reaction completion. Okay, so these are the different types of the indicators are also we can use based on this physicochemical properties. Now let us have type of the acid base titrations. Okay, so what are the different types of the titrations? We can see titration of a strong acid with a strong base. So whenever we are going to titrate hydrochloric acid with NaOH, that means strong acid, strong base, then how the titration curve is going to be present. So on x-axis volume of the base, that means NaOH is there. On y-axis how the pH is going to be present, that means pH how it is going to be increased. Okay, so point A means here it is C. Point A means here, that means no ml of NaOH is added, because here we have taken HCl in the conical flask and NaOH in the burette. Strong acid we are going to titrate with a strong base. It is going to give you the reaction of sodium chloride and water, right? So point A, that means no NaOH added, so the pH of the analyte in the conical flask is low. It predominantly contains the hydroxyl ions, that means H3O plus ions from the dissociation of this HCl, okay, hydronium ions, not hydroxyl, hydronium ions. Now we start adding base from the burette, that means we start adding the NaOH. Then what happens? The point B is going to come across. This is the pH recorded at a time point just before the completion of the neutralization is going to takes place. That is, here it is the B. Okay, that means whenever the equilibrium is going to start. So the pH changes are going to be slowly. Here you can see the change in the pH values. Now coming to the point C. Okay, here point C means this is the equivalence point halfway up the step curve. That is here. This is the equivalence point. Okay, so this is the here pH halfway of the neutralization is going to happen. So if you see the total curve, it is a very steep, right? So half of that value is going to be taken here as the equivalence point. So at this point the neutralization completely is going to takes place. The stoichiometry of the reaction is going to be completely takes place. Okay, so at this point what happens? The moles of NaOH added is equal to the moles of the HCl in the analyte. So H3O plus ions, and therefore the pH is neutral. Okay, so point D, that means the last point here. If you see, addition of NaOH continues, but the pH starts becoming basic in nature because HCl has been completely neutralized, and now excess of the OH minus ions are present in the solution. Thereby there is no change in the pH is going to be seen, right? So that means all the chloride ions have been completely neutralized by the strong base, that is OH minus ions. So these are the curves we are going to see while performing the strong acid with a strong base. Now let us see another curve, another neutralization curve, that is weak acid, that is CH3COOH, which is going to be titrated with a strong base. Okay, so CH3COOH, which is acetic acid, strong base NaOH is going to be there. So already we have seen this reaction before also. So sodium acetate is going to be conjugate base is going to be formed. Thereby you are going to see the point C at the halfway at the steep, how we are going to see the end point. So half of the pH you are going to see here. Okay, so the H2O ions are completely neutralized by the OH minus ions. Okay, so CH3COO H plus NaOH is going to give you the sodium acetate plus water. So the salt sodium acetate so formed dissociate into acetate ions and sodium ions. So this acetate, that means it is a conjugate base, reacts with the water to produce the OH minus ions, which increases the pH to the 9. Okay, so at the equivalence point, thereby you are going to see the complete reaction is going to be formed. Okay, CH3COO minus plus sodium is going to be ionization is going to take place. Thereby again it reacts with the water and it will give you the acetic acid plus OH minus ions. Okay, so thereby you can see due to the hydroxyl ions the pH is going to be increased by the 9. So that's why you are going to get the sharp end point also. Okay, because we are going to titrate with the strong base here. Now let us see one more, that is strong acid is going to be titrated with a weak base, that is HCl versus an ammonia. So NH3 plus HCl, it is going to give you the ammonium chloride. So at this point, how point C is going to be obtained here? The equivalence point at that is C, moles of the ammonia added equal to moles of the HCl in the analyte. Thus H3O plus ions are completely neutralized by the ammonia. Okay, so ammonia plus, if you are going to titrate with the hydrochloric acid, ammonium chloride is going to be formed. This ammonium chloride is going to react with the water and it produces the NH4 plus ions, thereby chloride ions, and which ammonia NH4 plus ions are going to react with the water, it produces the NH3 plus H3O plus ions. So this H3O plus ions, okay, so make the solution acidic, decreasing the pH to the approximately to the 5. Okay, so at the equivalence point, thereby you are going to see the sharp end point also for this reaction. Okay, so we know that if you are going to titrate with weak acid or strong base, or strong acid with the weak base, so you are going to see the sharp end points itself. But whenever the problem is with the weak acid with the weak base, so that's why the titration of the weak acid and weak base is not at all preferred one. So thereby in that case you can apply the Henderson-Hasselbalch equation also. Okay, so if you see the weak acid, whenever it is going to be titrated with the weak base, it is an example of acetic acid and ammonia. The equivalence point, you are not at all going to see the sharp end point here. Okay, so there is not at all steep in this plant. Here if you see weak acid and weak base, okay, so lack of any steep change in this pH throughout the titration renders the titration of weak base versus weak acid is difficult, and not much information can be extracted from this such a curve. Okay, so that's why even though we can perform weak acid with a weak base, but the end point is not at all a sharp end point you can observe, and information are also, it is going to be very erroneous results are also going to be observed. Okay, so that's why always try to use the above 3 types of the titrations for the acid base titrations only. Okay, so thank you students for listening this topic on acid base titrations.